Hi everyone, this is lecture 2 on ancient solutions to curve shortening flow. Let's recap what we've done last time. We defined curve shortening flow as the evolution of curves with speed equal to their curvature. This is following this equation here. And we talked about convex curves, and we discussed how a convex curve is determined by the curvature via this formula here, right? We can integrate using the turning angle and the curvature, and this gives us the curve. Now, the theorem we want to discuss today is the one proved by Hamilton, Daskalopoulos, and Sessom, and it classifies all compact, convex, embedded ancient solutions to curve shortening flow. And they are the circle and the angular oval. Okay, so as the curvature determines the curve, what we're gonna do is we're gonna look for function kappa theta t that is the curvature of a family of solutions, of a family of curves gamma t that satisfy curve shortening flow. Okay, and to do that, we're gonna use a function called the pressure function that is the square of the curvature. So we define P to be equal to kappa square, and we call this the pressure function. Okay, so we're gonna look for P equals P theta t. This will be our parameterization, and we're gonna parameterize so that these two variables are independent. Okay, so what we want to compute is PT, that is the evolution of the pressure under curve shortening flow. Okay, as P is equal to kappa squared, PT is 2 kappa times kappa t, and we know that we can compute the evolution of the curvature under curve shortening flow as kappa squared times kappa theta theta plus kappa. Okay, so this is equal to the evolution of the curvature under curve shortening flow. Now, I'm gonna write here at the side the derivatives of P with respect to theta, the first and second. Okay, so P theta is equal to 2 kappa kappa theta, and P theta theta is equal to 2 kappa theta squared plus 2 kappa kappa theta theta. And now we can write kappa theta squared, 2 kappa theta squared, sorry, as 1/2 P theta squared over P, okay, by using this equation here. And then I have plus 2 kappa theta theta. Okay, so plugging this equation of P theta theta here back to PT, we obtain that the evolution of P is equal to P times P theta theta minus 1/2 P theta squared plus 2 P squared. Okay. And I'm gonna name this evolution equation S star. Now, another quantity that will be useful is P theta. So we're gonna give it the name alpha. And we will again derive the evolution of alpha. So alpha is p theta. So I want to take the derivative with respect to t. Since t and theta are independent, I can switch them. And now I write what pt is from the equation star. And I need to take the derivative of this with respect to theta. Okay, now this gives me p theta 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 plus 4p theta. And that's it, because when the derivative hits this term here, and when it hits this whole term, the two terms cancel. Okay, and I can rewrite this as p alpha theta theta plus 4p alpha. Okay, so putting everything together, this gives me the evolution of alpha as p times alpha theta theta plus 4 alpha. And I'm gonna name this as double star. Okay, so these are the evolution equations of p and alpha under curve shortening flow. And we're looking for kappa such that kappa squared satisfies star. Okay, so we want to solve star. And we're going to do this by using the following ansatz. We're going to use that alpha t is equal to 0. Now remember that alpha t is equal to p theta t. So this is equivalent to saying that p theta, the function p theta t separates variables in the sense that I can write it as function of theta plus a function of t. And we will normalize so the integral of q over S1 is equal to 0. Okay, here, like if I add a constant to q, I'll still get a solution. So we're going to normalize so that the integral of q is 0. Okay, so how can we solve this equation star using this ansatz? Well, we're going to plug in p as q theta plus bt in star. Okay, once we do this, I'm going to skip the computation and write what we obtain. What we obtain is two different things. First, if q theta is identically 0, then this gives us the shrinking circle. Okay, so in the case where q theta equals 0, then the pressure is just a function of time. And it's not difficult by plugging it in star to get what B gives us, right? So if you look at star, all the right-hand side will be 0 apart from 2p squared. Okay, and you can solve, P is just B, and you can solve for B. And you get exactly the shrinking circle. Remember, that is the one that has radius square root of minus 2t. Okay, now, if q theta is not identically 0, then we can solve using star and 2 star. And again, this is just a simple computation, which I'm going to skip and write what we get. We get that q theta is given by alpha cosine 2 theta and bt is equal to alpha times hyperbolic cotangent of -2 alpha t. No, sorry, not alpha a, I mean. Okay, and this is for t less than 0, and a, capital A, some positive constant. Okay, what does this mean? This means that my kappa, which is the square root of p, is equal, and it's positive, right? Because we're looking for convex, is equal to square root of a times q plus b. Yeah, well, equal to square root of q plus b, which is this, plus hyperbolic cotangent -2 a t. Okay. Now this a here is just a scaling factor. So changing a, we get the same solution, but just that they differ under scaling. And for the special case, when a equals 1, the solution can be written as cosine x equals e to the t hyperbolic cosine of y. And if you remember from the first lecture, this is exactly the angular oval. Okay, so here, what we've done in the first lecture, we've already said that the angular oval is a solution. Here, we presented another way to show that, well, we presented a way to show that the angular oval is a solution. In fact, we did show that any solution for which the curvature can be split into a function of theta plus a function of t has to be the angular oval. Okay, but of course we use this ansatz. We said we look for such solutions, right, whose curvature can be, the pressure function can be split this way. Okay, so the theorem now we want to show, the Hamilton-Scalable theorem, is that there are only two solutions, the circle and the angular oval. Okay, there are no other solutions that do not split the pressure function this way. Okay, so let me write again the theorem. There are only two convex, compact, ancient solutions to curvature. The shrinking circle and the angular oval. Okay, and remember we talked in lecture 1, what do we mean when we say only two? Well, this is always modulo the symmetries of the equation. Okay, so no parabolic scaling, the spatial rotation, and space-time translation. Okay, so we're gonna give an idea of the proof. Right, recall for our notation that alpha is equal to p theta and p is equal to kappa squared. Okay, p, the pressure function, is the square of the curvature. Alpha is the derivative with respect to theta of the pressure function. And we define the following function, which we name as I alpha. This is the integral over S1 of alpha theta squared minus 4 alpha squared d theta. Okay, now this is not randomly chosen. This is chosen because on the angular oval, we have that p theta t is equal to 0. Not just on the angular oval, right? This is also and on the circle. We have that this is true, okay? This is what's the ansatz. P theta is alpha, right? So this is the same as saying alpha t is equal to 0. Okay, now if we go back when we computed the evolution of alpha, this is equation double star here. Okay, we have that alpha t, this is equal to p alpha theta theta plus 4 alpha. Okay, this is double star here. Okay, and therefore, when I look at I alpha and I apply integration by parts on the first term, I'm gonna get integral of minus alpha times alpha theta theta minus 4 alpha squared d theta. And now this is minus alpha theta theta plus 4 alpha. Okay, so this is equal to 0 on the angular this is equal to 0 on the angular oval and on the circle. Okay, this is a first observation. That's why we pick this I alpha. And now, what are we gonna do for the proof? Here are the steps we're gonna follow. So we look at this integral, this functional for an ancient solution. Always convex and compact. And the first thing is to show okay, di dt, compute this and get that this is equal to minus 2at squared over p d theta, okay, over S1. Now this, of course, is less or equal than 0, okay? P, remember, is always positive, is kappa squared, and I have at squared, this is positive, and I have this minus sign, which makes everything less or equal than 0. Okay, so we showed that this function is always non-increasing along a flow. Well, the flows we are considering, right? Ancient, compact, convex. And the second is to look at the limits of I alpha, first as t goes to minus infinity, and then as t goes to 0. And we will show that the limit as t goes to minus infinity is less or equal than 0 whereas as t goes to 0, it's bigger or equal than 0. Now we have something that from less or equal than 0 becomes bigger or equal than 0, but it's also non-increasing. So this means that I alpha has to always be 0. Okay, so now 1 and 2 imply that I alpha, well, not claim, let me just, right, let's note that 1 and 2, they imply that I alpha t is identically 0, and of course the I dt also 0. But if you look at 1, since the derivative is 0, this implies that alpha t is equal to 0. Okay, but this was our ansatz, and when we were looking for solutions that satisfy these ansatz, we showed that the only two solutions we get are the angular oval and the shrinking circle. Okay, so this implies the Hamilton-Daskalopoulos theorem. Okay, and this finishes the proof, as long as we have proved 1 and 2. Now, 1 is just a computation. So I'm gonna leave this to you to check. And for 2, let's name the first direction A and B. So for 2A, where we want to look at the limit as t goes to minus infinity, we will do the following. We will define another function, where I'm not going to call jt, is the integral of alpha squared over 2p. Now I'm going to write this as, this over as 1. I'm going to write what is alpha, this is p theta over 2p. Okay, and note that this is bigger or equal than 0. Now, why we define this integral j, this is chosen so that its derivative is almost close enough to minus I. And when I say close enough, this in the following sense. So if I look at dj dt, okay, this is equal to integral to alpha t over 2p minus alpha squared 2p squared times pt. Now, remember that this has been computed, and this is equal to p times alpha theta theta plus 4 alpha. On the other hand, there's pt here. This is equal to 2 kappa t, and this kappa t, kappa we know is positive because it's convex. Kappa t is also non-negative. Why? This comes from Hamilton's Harnack inequality. So by Hamilton's differential Harnack inequality. Which is a very powerful tool and says that if you have a compact convex ancient solution, the curvature is always non-decreasing. Okay, this is also true for higher dimensions, very powerful too. So using this second term is less or equal than 0. I can throw it away and write this as less or equal S1 alpha alpha theta theta plus 4 alpha squared. Okay, I've replaced AT. And now the right hand side, by using integration by parts, is equal to minus alpha theta squared plus 4 alpha squared, which is equal to minus I alpha. Okay, so the derivative of J is bounded above by minus I. Okay, so now we can take this inequality and we integrate between T1 and T2. Okay, what do I get? Minus integral from T1 up to T2 of I alpha. This is bigger or equal than J T2 minus J T1. Remember up here, we've seen that J is bigger or equal than 0, so this is bigger or equal than minus J T1. Okay, and I'm gonna write this again and write that integral from T1 up to T2 of I alpha is less or equal than J T1. Okay, then we're gonna let T1 go to minus infinity, and we claim that the limit of Jt as t goes to minus infinity is finite. Okay, so I want to let T1 in this equation go to minus infinity, and I want to show that the right-hand side stays bounded. Okay, let's assume for a second the claim. Then what happens? Well, that's right. That claim implies that integral from minus infinity up to T2 of I alpha is finite. And since I is non-decreasing, we must have that I alpha t becomes less or equal to 0 as t approaches minus infinity. Okay, else there's no way that this integral here is finite. All right, so we're left to prove the claim. Okay, now why is the claim true? Remember, PT is bigger or equal than 0. That comes from Hamilton's Harnack inequality. Okay, this is kappa t, kappa times kappa t, which implies that 0 is less or equal than integral pt over p. And I'm gonna write what I get as pt, which has been computed. Okay, this is P theta theta minus 1/2 P theta squared plus 2P squared over P. Okay, the first term, P cancels, and I have integral of P theta theta. This is just 0. So I'm getting integral of minus 1/2 P theta squared over P plus integral of 2P. Okay, this, remember, is bigger or equal than 0. And this first term here is 1/2 JT. Okay, so minus 1/2 JT. So if I bring it on the left hand side, I get that JT is less or equal than 4 integral over S1 of P. But this here, remember, P, right, is kappa squared, and kappa is non-decreasing. So this guy here, this integral, is non-decreasing again by Harnack. Okay, Hamilton's Harnack inequality. So as we let time go to minus infinity, this becomes, if not better, it remains bound. Okay, so this implies that the lim sup of JT is t goes to minus infinity. This is always bound, which is what we wanted to prove. Okay, so this almost finishes the sketch of the proof. Now let's go back to our first diagram up here. So we said that 1 is just a computation. For 2, we had to find the limits of I, and we described this bit here, how the limit of I is negative, is less or equal to 0 as we go to minus infinity. For this, I'm gonna skip this one, it's a little bit technical, but the idea is that here we use the fact that as t goes to 0, the solution shrinks to a round point. Okay, so this part here, I'm just gonna make a note at the end. So 2b can be derived using the fact that as t goes to 0, the solution shrinks to a round point. This is a result to a round point. This is a result by Gage and Hamilton. Okay, and without being too technical, the point here is that not only do we know that the solution shrinks to a point, but we know the rate is shrinks to a point. Okay, so blowing up now, as we let t go to 0, everything collapses to a point. But if we rescale so that, like, zoom in, this is like an example of a zooming in a singularity, we do get a shrinking circle as a blow up limit. And using this fact, we can obtain information about the behavior of this functional I as t goes to 0. And it turns out that it has the correct sign, and we have the two inequalities that we want. And this completes the proof of the Hamilton-Daskaloglu assessment paper. So I'll stop here.